So very good morning, one and all. Today we are going to take the subject of electromagnetic field theory, where Prof.Sumera Ali is. We are going to continue the chapter today, the uniform plane view. So in the first session, we have studied about the introductory part of your electromagnetics. In that, we have seen the vectors, we have seen the Maxwell's all the equations. We were also done the Gauss's law. Okay, so the numerical which are related to the Gaussian, the numerical which are related to the boundary conditions, the numerical which are related to the Maxwell's, all we have done, even the numerical which were related to the vectors in vector addition, vector subtractions. Likewise, all we have done in the last unit, you may say. Now this is the unit number 2, which is on the uniform plane view. Okay, so we will see first here the theoretical part related to uniform plane view. So what is that uniform plane view? What are the objective behind that uniform plane view? Why we are learning this uniform plane view? In short, I have mentioned here, that is, this uniform plane view is nothing but the solution to the Maxwell's equation. We are aware from that we are having the Maxwell's 4 equation in the form of an integral as well as in the form of a differential. Okay, and even this Maxwell's equations are classified in the what you can say electrostatic, or you may say the electric field as well as the magnetic fields. Okay, in the theoretical part of our boundary conditions also we have observed the Maxwell's equation, 4 equations. Maxwell's first, second, third, and the fourth. So in short, you may say this uniform plane view is nothing but the solution to the Maxwell. Whatever we will simplify the numerical which is based on the Maxwell, so you can say the 4 equations which are related to the Maxwell, that can be the simplified with the help of this uniform plane view in short. So what is that uniform plane view? So in the time, we know very well the time domain and the frequency domain are the 2 domains which affects or simplify the numericals, or you can say whatever the wave will be propagate, that we can concentrate either in the form of the time domain or in the form of the frequency domain. So here, if you're talking about the time domain, so you may say that the lossless medium will be there. Anyhow, we are aware whenever the signal is passing from the transmitting to the receiving, medium will be there in the free space. So every time during that period, we should also focus on the one of the parameter, that is nothing but the lossy or as well as the lossless. Okay, or you can say the lossy medium, or you can say the lossless mediums, because we should also think about these 2 major parameters. It's not like if you observe practically the same amount of the signal will be received by the receiver. No, ideally it's possible. Whatever you are transmitting from the transmitter antenna to the receiving point, you may assume the whole 100% the signal is received by that receiving antenna, but practically it's not possible. Definitely for the medium, and that to losses will be in there will be interference of the noise, there will be the losses. Okay, all these things parameter we need to consider while we are going to simplify any kind of numericals related to the Maxwell's, related to the other, or maybe the uniform plane view. So here we should concentrate about the 2 points. One is nothing but the time domain. Okay, that is for the lossless medium, and second is nothing but the frequency domain for the lossy mediums. Okay, so come to the point, that is nothing but the name of the chapter itself indicating uniform plane view. So what is that view? View is nothing but the pattern values in the space that appears to move as the time involves. Definitely, we know very well, while I am concentrating, my wave is traveling or my wave is propagating. So definitely first will come in my mind, my wave will be the sinusoidal waveform. If I am saying my wave will be in the sinusoidal waveform, so definitely you may say what we can say with respect to the time period, whatever the parameter you are considering, so that should be with respect to the time period. Okay, so the time involvement will be there, time will be evolved. Okay, so even though we are concentrating on the voltage, even though you are concentrating on the current, or you may say the power, But the thing is that you should focus on the additional point, that is nothing but the parameter is the time. The role of the time will be a major role. The time will plays the major role while you are going to calculate, or while you are going to mention the wave equations. Why we are saying the wave equation? Because in this case we should able to write the equation which is related to the voltage, the equation which is related to the current. If you're writing the voltage and the current, definitely the power, indirectly the power equation will be there, because we know very well why you're thinking about the sinusoidal, the wave will be travel. Okay, the wave will be travel at the top, the voltage, either the voltage or the current will be there with respect to the time period t. So here continuously at each and every instant, what the thing is going on, how my wave is traveling at every instant, that I need to measure. So simultaneously I need to write my equation. Okay, just like I need to apply the limits, I need to derivate the equations. Okay, each and everything is needed. So what will be my limits, whether it will be the 0 to pi or 0 to 2 pi, how the things are going on. So that how you can reflect with the help of your the wave equations. So similarly, few examples are listed here in the wave. What mean by that wave? You can say, so include the what waves, sound waves, tremendous waves are there here. Few are listed. That is your water waves, sound waves, seismic waves. You know very well that is a voltage, current, and other waves are there which we required, or you can say at the transmission line. So definitely this wave will be travel from the one point to the another point, and we will get the you can say the output or the result. Okay, so in the next overview, so here again, the wave will results in the form of the exchange between the two different form, okay, of energies. We know very well from one transmitting to the another, my wave is traveling. Definitely that there is an exchange of the energy from one point to the another point. Okay, and all these things are going on with respect to the time period. So in short, we can say the time rate of the change in the one form into the other form. Okay, so in short, you can say every time my time will be affect for my signal. Okay, for my wave, you may say. So here, if a wave is concentrating, if you are going to concentrate that wave, definitely the time rate of the changes from the one side to the other side you need to bother. So how the wave will be possessed? The wave will be possessed if there is no mass, if there is a energy, there is a momentum and the velocity. If these parameters, if you are going to observe, you may say that you are the effect of the wave will be there on that particular signals. Okay, so now come to the point. What is just now in the previous slide I have explained you. We are bothering about the two major points, that is nothing but the time domain, and other is nothing but my frequency domain. If you are talking about the time domain, so definitely the Maxwell, how we can write the Maxwell equation in the differential form, because we are aware the Maxwell equations are in the differential form as well as the integral form. Okay, and that too you may observe one additional point, that is nothing but the dot product and the cross product. Already we have studied in the vectors. If dot is there, what will be the conditions? Okay, how my directions, if they are multiplying with the dot, so what will be the effect? If they are directions are different, so what will be the effect in the form of a zeros and one? We have studied. Even if there is a cross product, how my matrix will affect, that is ax ay is a direction, and that to row wise. Okay, so this will while we are focusing on the time domain, you should be aware from the back history of how I got that dot product, how I got my cross product, how I can simplify my the equations. Okay, so because while you are playing with these what we can say the equations, okay, or you may say the Maxwell's equation in the either the differential or integral, whatever, or the you while you are going to simplify the derivation, that time you should know aware from all the back history which is related to your the vectors and all. Okay, which is required. So see here, how my Kc and the Ki are affecting. K is a constant term. Here the conductivity and the current is there. Here the cross product, where the del is nothing but the dou term, you know very well, dou by dou x plus dou by dou y plus dou by dou z. Okay, if you're talking about the x, here will be the ax, ay, and az. If there is a E, so definitely my dou by dou x will be with E. Okay, electric field intensity E, and here magnetic field intensity. So these two are in the cross product, and how we can get with respect to the time period, so that is a dou B by dou T, where a dou B is nothing but here magnetic flux density, the magnetic field, whereas a D is nothing but the electric flux density. Okay, with respect to time period we are considering, and these two are nothing but the current densities. Okay, K and the J is are nothing but the current densities. Okay, one will be reflected in the electric field, other will be reflected in the magnetic field. Okay, just like K will be the combination of a Kc plus Ki, here will be J will be the combination of a Jc plus Ji. One will be reflect here the, if current density here there, then the definitely the conduction current density will be here. Okay, so here the dot product, that is a del dot of T. Here we are having that charges, or what we can say the equivalent charges you may say, and the momentum will be here with respect to the velocity. So D represent in the electric field, B represent in the magnetic field, both are the flux densities. Okay, this is nothing but this is nothing but in the electric, and this one is nothing but the magnet. So in this way you should aware from these basics equations which are related in the if we are seeing the time, that definitely only the dou by dou T is will be the additional part. So similarly here in this again the Maxwell equation in the differential form, how we can write what will be the effect of my D, what will be the effect of my B, what will be my JC and the KC here. Okay, so what we all already we are aware, we have studied this electric flux density D is nothing but your the epsilon. E epsilon is a permittivity, and the E is nothing but electric field intensity. Okay, this D will be measured in the coulomb per meter square, whereas E will be measured in the volt per meter. Similarly, if you're talking about the magnetic field, why we are writing all these formulas? Because these are required in the further equations in the Maxwell's. Okay, so always you must aware from the basics laws or basic formulas you may say. So B will be equals to mu H, where mu will be the permeability. Okay, means you should think about the medium. Okay, or you can say atom media interface. What will be the constant parameter? So that time permittivity and the permeability will affect. Permeability will be affecting the magnetic bond. What we can say the magnetic fields, whereas the permittivity will be affecting the electric field. Okay, so likewise the JC here, again what will be the case of JC, and or you can say at the place of JC what you will be substitute. So here you may say this is the current conduction density, and this is nothing but the sigma, that is the conductivity, and E is there. So this is the formula of simple J, that is J will be equals to sigma into E, that is the conductivity into the E. Similarly, this is also the current what we can say current sheet in the form of a density, here in the form of the intensity, here the density, here will be the electric field, here will be the magnetic field. Okay, so see here this will be the again in the magnetic field, that is a what we can say the sigma, but in the magnetic field, that is the M. And with respect to the H is nothing but electric flux field intensity in the magnetic field. So likewise you need to substitute the values in. Okay, in the previous we have seen, and similarly here what we are doing additional part, we are substituting the value of mu, we are substituting the value of the epsilon, we are substituting the value of the J, we are substituting the value of the K, likewise, because all these four formulas are required while you are going to derive or simplify the numerical. Okay, so you should remember how I can substitute my value of the mu, because we know very well mu will be equals to mu 0 mu r. Mu 0 again the 4.2 10 raised to the power minus 7, and mu r it's depending upon the medium what you are going to use. If mentioned in the numerical, okay, you can substitute. If not mentioned, you may assume like the air or other thing. Okay, so likewise the epsilon will be here, epsilon 0 epsilon r, epsilon 0 will be 8.854 10 raised to the power minus 12. Likewise the epsilon r for the air, it will be the 1. Okay, so depending upon the material, these mu and the epsilon will be you can mention the values, okay, by concentrating the constant value and other parameter mentioned in the numerical. Similarly, you can substitute the D, the B value, the JC and the KC. Okay, so here this one is a representation in the cross product, whereas this one is a representation in the dot product. Similarly here in the time domain, if your medium source, or you can say the free space is there, and the lossless medium is there. We remember lossy, lossless, conductor, dielectric medium. So all these you should keep in your mind. There are various kinds of conditions that you need to apply, exactly how my wave is traveling, or in which condition my wave is traveling, or through I am sending my waves, like whether the conductor is there, whether the free space is there, whether the dielectric is there, whether the lossy is there, or lossless medium is there. So all the medium you need to concentrate while you are going to simplify the numerical. Similarly here, if lossless is there, they mention clearly the condition, that is a Ji, or you can say the Kij will be in the electric field, whereas K is in the magnetic field. Both will be equals to 0. Similarly, this charges in the momentum or the velocity form. So here they are also 0 in the what you can say electric as well as in the magnetic field. The conductivity or the sigma is again the electric as well as the magnetic will be treated as a 0. So while you are substituting all, or you can say while you are going to apply the condition by substituting the 0 wherever you will find this value. So at that time, finally the conclusion will be other part will become as a 0 and the rest of the part will remain. Okay, if you are going to substitute these 0 values. So if a lossless medium is there, in the cross product, or you can say the lossless medium for the time domain, the cross product will be minus mu. Why minus? In the previously there were something, and but by substituting these value for 0, it here will be the 0 minus of so and so. So likewise 0 never affects, so that's why no need to write here the every time to 0. Likewise we have found by applying a book condition only the minus mu dou by dou t, but in the magnetic field that is nothing but the h. Similarly the vice versa. Okay, if you're treating the input is here, then output will be in the form of magnetic e to m. Okay, or m to e, likewise vice versa. Getting? So if here magnetic field is there, definitely mu will affect. If electric field is there, epsilon will affect. Similarly, in the dot product, that is del dot E, that will be the 0 in the lossless medium, and the del dot H, if there is a dot product, definitely this will be loss in the lossless medium 0. So here the little bit derivation is there. For right now, we are not focusing on the derivation part. Okay, so just simply how we got this one by observing how my wave is propagating from the transmitting antenna to the receiving antenna, and which components are affecting, which mediums are affecting. By focusing in all the respect of all the points, we are trying to derive again here the cross product of the Maxwell's equation del del. If twice we are going to multiply, okay, if in the entire, so definitely this del dot del will be square term. Okay, so here I am not focusing how to derive that expression. Simply we remember the previous slide was important by concentrating the point of lossless medium, this point. Okay, now come towards the next, that is a wave, how we can write the wave equation in the electromagnetic waves if you are having the source of the free space of the lossless medium. Here also there is a repetition. Why there is a repetition? If we are thinking about what we can say the lossless medium, and we are focusing the E and the M simultaneously. If you are talking the individually, that is if I am bothering about the electric field, I will write my equation in the electric field. If I am bothering about the magnetic field, I will write my equation in the magnetic field. While you are focusing on the both, that is electric as well as the magnetic, and that too transmitting and the receiving, both the point, if in all respect if you are constrained, then definitely that will be the del square term will come in the picture. Because not only in a simple way, we need always take a electric field, then later on the magnetic field, and that too at the beginning we focus on the transmitting, then later on the receiving, likewise. But whenever if you are focusing in all respect, that is electric field, magnetic field, and that too what we can say electric and magnetic, and all the condition, if you're applying simultaneously, that is the transmitting and the receiving, both if you're both in that time, this square term will be come in the picture. So here del will be then del square of E here. What we have done, the electric and the magnetic we have separate out. Okay, the wave equation. So whenever usually if you are going to solve the electric field wave equation and you are going to determine the H and the E, so that is possible with the help of Faraday's law. Okay, so how we can write that Faraday's law? Already we have seen in the first chapter also what will be the effect of MMF. Okay, how that north and the south pole will be attract on the conductor, and how my fluxes will be linking. Okay, so with the help of by keeping all the fundamentals that we can apply while you are going to simplify equating this equation, so you will conclude that is nothing but in that is the H and the E in the by using the Faraday's law. That's it, del square E minus of mu epsilon dou square here. Dou square here, if you observe this mu and epsilon, you will be able to observe that you will be able to find the electric and the magnetic medium we are considering. See here, the source will be the free space medium is there, then definitely we are thinking about both the things. That's why we are taking here. If you are going to simplify this term, the other term will be 0. Here, if you're focusing in the magnetic field, but the medium will be the both. Okay, you are starting with the magnetic field, but medium through the medium, that is a electric and magnetic field, and you are going to simplify this magnetic effect, then you will be able to find that will be equals to 0. So now here, how we can write the basic what we can say the equation of electric field intensity if we are talking about the uniform plane wave. Okay, if you are talking about the uniform plane wave, what will be the effect? So in the uniform plane wave here mentioned, that is in the electromagnetic waves in which the electric as well as the magnetic fields and the direction of the propagations are mutually, so that time how my amplitude as well as the phases are the constant over the plane. Okay, and how we can find that particular direction while you are going to propagate that thing. So sir, just imagine here or just assume, examine here how I can write my wave solution. So here electric field is there, and this electric field, you may say what we can say, you are talking about the, if you are keeping in your mind that is a reference point, that is x, y and z coordinates. We remember of a Cartesian or this what we can say rectangular coordinate system. uh, all of you pay attention, that is a what we can say rectangular or a Cartesian coordinate system. So in the Cartesian coordinate or rectangular coordinate system, you will be able to find that just a minute, I have lost this property. So here, if you pay attention, so you will be able to find my z will be in the vertical. We remember that figure in the Cartesian of the rectangular. So z was the vertical, x was the slanting, and the y was the horizontal. So here we are interested in the time. That's why this equation, same equation, we can write in the form of the with respect to the time period. So how I can focus my x is additional, or you can say I'm right now I'm focusing on my x parameter, but my z is the vertical, so perpendicular on a slanting, the z is on a z direction, you can say my x is a slanting and z in the vertical form, and with respect to time period I am going to concentrate. Here will be my unit vector. Why I am taking unit vector? Because I am focusing on the x, that's why here will be ax, electric field intensity at a x direction, and that x direction is linking with the zy, that is perpendicular, because z is a vertical and that will be perpendicular or somewhat connected to that x. And why we are taking with respect to time period? Because we are interested in the uniform plane view. So similarly, the wave equation for this, you can apply the Maxwell's equation. How we can apply the Maxwell equation in the x direction? So here just because of the del square, we are taking this a dou square, and we are taking with respect to the x, that's what ex. And here the that is z is a vertical and that is reflecting on the x, that's why dou by dou z will be the common, whole square will be the common just because of the del square, and es we has particular one, and the medium will be the electric as well as the magnet. So the permeability and the permittivity both will be act. Again, with respect to time period we want, because in the bracket ex comma sorry z comma t was there na. Z comma T. So here was the Z and here was the T, and with respect to which one, that is nothing but my X term. That was in the both the side X, and the X is here, but here Z and the T, just because we are my particular this X will be dependent upon the Z as well as the T. So this will be the general solution of your the wave equation. If you're talking about why this here the P1 and the P2, this P1 and the P2 ultimate, if you are going to write the equation of the voltage, equation of the current, so definitely I will get my power, that P is equals to. So here, while you are going to find out the solution, so you should think about the average power. So one of the derivation is on this on the basis of uniform plane wave, that is nothing but, that is in later on, that is nothing but the Poynting theorem, or you can say the average power density. Okay, how we can find my average power while I'm writing my equation, or simplifying or reducing my equation in the form of the voltage and the current. So ultimately I'm talking about my power. Okay, so here the P1 and the P2 are nothing but the two equations which I am going to receive from the electric voltage in the form of the voltage and the current. So that's why here, see here, so T Z comma T is nothing but my this X. I'm at a particular thing. Okay, I'm at particular thing, and I'm focusing or dependent upon this Z and the T. T is with respect to time period, just because of the uniform plane wave, and Z is nothing but the vertical parameter, okay, which is connected to my X. But if you're talking about the power, so here either two powers are there, P1 and the P2, two powers are there. Okay, one power will be affected with Z, and one will be affected to the T. So here, how I am taking this Z minus VPT, that is nothing but here, what is this V? That is nothing but the voltages. Okay, voltages at a particular potential, or you can say the, in short, peak voltage, you may say. Okay, in many of the textbook they're referring. Okay, Z is the, again the direction, or you can say the parameter of Cartesian coordinate. T is a with respect to time period. So see these two equations, these are the two functions that you can write while you are going to simplify the uniform plane wave and the wave is propagating. And this plus or minus, obviously, if Z is a, what you can say, the what you can say, vertical. So if you are thinking about the top, the definitely positive. If you are thinking about the bottom, that definitely that Z will become as a minus Z, because of the direction, or you can say. Okay. So in this way, we can determine the wave equation of a magnetic field, okay, by using the Maxwell's equations. So here, one of the, that is just not the velocity or the potential or the peak voltages that we can find with the help of this equation, ultimate with the help of this sources or the boundary conditions, that is the P1 and the P2. We know very well this velocity of propagation is nothing but 1 by root of mu and epsilon. These are, if mu is there, mu 0 mu r will be there, and epsilon is there, mean epsilon 0 epsilon r. So mu 0 and epsilon 0 constant value you have with you. Okay, but the epsilon r and the mu r, that depending upon the numerical, or depending upon the medium which you are going to use, you can substitute that value and you will get the, that is nothing but the velocity of propagation. Okay, these things are required for the simplifying the equation. Similarly, in the previous case, we were interested in the electric field. Here we are interested in the magnetic field. That's why we have written this equation on the basis of a magnetic field. So if you're talking about the magnetic, definitely E will be replaced by the H, and the D will be replaced by the P. Okay, because E and the D are in electric field. E comma D are in electric field, whereas H comma P are in magnetic field. Okay, so here H will be equals to, again the unit vector is taken here. If if I'm concentrating, my electric field is on the x-axis, so definitely I should think about my magnetic field is on the y-axis. That's why here the y is taken. I think in my introductory part of a slide, so one of the slide, the wavelength, how I have calculated in the 3D the wavelength. So at the time I have shown, if my x is, if you are thinking the x is electric field, the y must be the magnetic field, or vice versa. Doesn't matter what you are taking, but whatever you are taking, that should mention the assumption, okay, at the beginning. So likewise, E was in the x, so H was in the y direction. Okay, similarly we have tried to simplify. What is the additional here? Additional part is nothing but 1 by eta. Eta is nothing but the intrinsic impedances, and that matters. Why matters? One of the point was there, that is the impedance matching. I hope you have remembered that point in the network analysis. Uh, while the load is there and the signals are transmitting from the transmitting to the receiving antenna, that time we are interested in the AC analysis. That is how my load is matched with the previous one, or in short, the transmitting and receiving impedances are matching or not. So here also in eta is nothing but intrinsic impedance for match. So this intrinsic impedance of the medium can be calculated as eta is equals to root of, these are the standard formulas, eta is equals to root of mu by epsilon. And again we are aware mu is nothing but mu 0 mu r, epsilon is nothing but epsilon 0 epsilon r. Okay, likewise you can substitute while you are going to simplify the numerical. So we have formulated two formulas, the velocity of propagation as well as the intrinsic impedances, and both are the independent of the sources, you may say, and which we can determine only by the properties of medium. Why we are thinking about these parameters, that is the eta and the Vp, just because of the medium. Similarly, if you talk about the velocity of the propagation of a light, definitely we are aware from the in the free space, you can say the light propagation or natural light, that is a 3 into 10 to the power 8 meter per second. And also we are aware the constant value of the eta. Okay, if you are thinking that medium is the free space, if you are thinking the medium is the free space, otherwise what we need to do, we need to eta will be equals to root of mu by epsilon. Mu will be mu 0 mu r divided by epsilon 0 epsilon r. Okay, and you will substitute the value of mu 0 4.2 10 to the power minus 7, and the value of mu r if given, then okay. If not given, you need to concentrate which medium you are going to use, whether it's a free space, whether it's a dielectric, okay, which medium you are using, whether it's a lossy, lossless, whatever. So accordingly this eta will be there. So if you are thinking about the free space, so definitely my eta will be this after simplification, root of mu by epsilon. After simplification, you will get 125, or that will be equals to 377. This directly you may take if numerical is mentioned, and in that numerical they mention the medium as a free space. That time directly you can substitute the value. If velocity is not given, other parameter of velocity is not given, then you may take directly, you may assume directly the velocity will be the 3 into 10 to the power 8, whereas in intrinsic impedance you may take directly 377 ohm.